Hello everyone, good afternoon. This is Ivan from EPIC, the largest photonic industry association in the world. And today we prepared something very special for you. We're inviting you to join us on a virtual live tour for one of the largest EPIC members, STMicroelectronics. We will visit one of their facilities to get a sneak peek of their technologies and give you an exclusive opportunity to talk to the engineers developing some of the most desired high-tech products on the market today. STMicroelectronics is of course a giant company with a turnover of $10 billion, 43,000 employees, including more than 8,000 people working in R&D. During our virtual tour today, we will only visit a small but very important part of their facilities. We're going to the R&D center of STMicroelectronics, located in Tel Aviv in Israel. Let me remind you that STMicroelectronics is a world leader in MEMS, microelectromechanical systems, including MEMS sensors and actuators such as micromirrors used for laser beam scanning. Today, we visit their laboratory in Tel Aviv, explore the technologies that they're developing there, and we observe two of their exciting products in action: the augmented reality smart glasses and LiDARs for advanced driver assistance systems and for 3D mapping. With that, our guides today will be Dadi Sharon, the R&D manager of STMicroelectronics in Israel, and Ilan Ruth, the director for marketing and business development. With no further delay, I invite you to join me in this exciting virtual tour that is going to start now.
I hope that you have seen Dadi saying hello at that point. Dadi's going to help me with the camera and also with the tour. I wanted to start with showing you some of the prototypes and products that we have worked on for actually 10 years. So if you can have a closer look here. It started with a device that was quite popular about 10, 12 years ago, which was called the big projector, with the idea of being able to have a very small picture that you can put in your pocket or even embed it into kind of a smartphone or telephone that didn't really exist back then, in order to share, really able to have some kind of media sharing capability that didn't exist back then, because telephones or stuff like that had very small screen size. The beacon projector market didn't really succeed in pick up, but the technology actually found its place in other types of application and devices that we can see over here. For example, we're talking today augmented reality, virtual reality, mixed reality, basically some kind of a head-mounted display, a wearable device. We are working here at ST on the next generation of smart glasses, all-day wearable, and where we build basically the display engine in order to come up with the smallest possible display engine that exists today in the market. So if we look, for example, at technology, so it started with this module or optical engine with micro mirrors, and you can see here a very big size of a laser dot, which is a green dot. This one was in 2008 when green laser diodes were not even available as direct native one. This one was basically a double charge red in order to emit. And this is what we can see the difference in size over 10 years, where today we're using a light source with red, green, and blue all packaged together, thin film-based micro mirrors, and all the different optical elements inside, about 1 cc compared to about 7 or 8 cc 10 years ago. So this is what technology can bring you in terms of integration. Besides working on augmented reality, using the micro mirrors for display with red, green, and blue laser in a raster scanner kind of mode, there are additional markets that are interesting for the use of micro mirrors, such as this device, which comes from Intel. It's the Intel RealSense, second generation. This is a depth camera for consumer goods. It can detect objects up to around 10 meters with a very, very high resolution time of flight. And there is a micro mirror inside, a micro mirror that is biaxial that we have developed Intel for this application for time of flight. This one is using non-visible light. This is infrared. While the application for augmented reality as a display, of course, uses visible light in the wavelength of red, green, and blue. So different kinds of devices and products and prototypes that we have done up to now. ST is the world leader in MEMS in general for sensors and motion sensors, accelerometer, gyroscope, pressure sensors, temperature sensors. But actuation, we are one of the biggest world maker of the fluidic actuators, for example, for printers. And micromirror is also kind of an actuator. And we're going to see the development kits around it, the uses of that micromirror, the prototyping of, but we will start first by visiting our electronics engineering lab. We will have a look on the architecture. We'll have a look on the different kits in terms of PCBs and boards that we have. And then we will see, of course, a live demo of a projector on a wall. So follow me, Daddy. Let's visit our friend Jacob, which is waiting for us in the electronics engineering lab. Hi, Jacob. Hi, Kobe.
Hi, everybody.
Would you present yourself and
Sure.
start with explaining to us, before going and diving into the actual hardware that you have over here, quite a set. Let's start with something which is, an upper layer, the architecture of this solution.
So, hi, everybody. My name is Jacob Lefkovich, and I'm working at ST as the hardware manager of the site. I'm excited for the lab. So, we'll start in me explaining to you the block level diagram about the laser beam scanner system.
Excuse me, Jacob. Can we move the camera a little bit closer so that we can see that block diagram?
Sure. Now it's okay?
Much better. Thank you so much.
Sure. So again, I will explain to you about the laser beam scanner based on the thin field PVT MEMS. So we'll start with the main building blocks of our chipset. The block diagram is divided into two. We have a PCB with all our ASICs, and we have an optical engine. So, and I will explain to you how an image that is stored or generated in the application processor will be projected as a 2D image on the screen. So we have a pre-distorted image that is stored or generated in the application processor that is connected to our video data path IC through a MIPI 4-link DSI. It converts it into a 10-bit dedicated interface to our LVD. The LVD is our laser driver. It's a current sync laser driver. Then it's connected to the free RGB package. There's a diode. And inside the optical engine, we have optics to shape, focus, collimate, and combine three lasers into our fast PCT mirror. And PCT mirror is a resonance fast mirror and draw on the that creates the 2D image. We are in a closed loop, and we have for drive and control the two mirrors, a mirror, drive, and controller IC. And it sends in real time the movement of the mirrors. We have a PZR sensor inside. It shows and monitors the frequency and fix the opening angle. Also, to maintain a white point, but a white point that will not move in temperature, we have inside the optical engine a PD, power detector, that is connected to the LVD. And finally, we have an STM32 CPU that is controlling calibration chip that is connected to the application processor. All power of the chipset is around 320 milliwatts. That is projecting in real time the image on the wall. And you can see the laptop screen with the pre-distorted image. Elon, can you turn on the? And now we'll go to the real hardware. Here you can see our development board with the chipset that I was explaining about in the whiteboard. So we have the laser driver, the controller of the mirror, and all the other chips. Here we use an HDMI to MIPI bridge, and we have a board-to-board connector to plug in daughter cards like an application processor. And here you can see another board. It's a form factor development board. It's a 60 on 10 millimeter with the same chipset that is suitable for the smart glasses application. So in ST, in the site, we do a full life cycle of hardware development from spec to a real proof of concept. And we also develop and produce calibration and characterization boards for our ICs. And here you can see the different boards that were designed and manufactured here. So we have rigid, we have flex, we have rigid flex, all the different technologies that are needed for the client.
This is really impressive. So I love the block diagram and the very, very small form factor for the glasses.
Thank you. Indeed, indeed.
Indeed, this is great. I was wondering, with the same approach, can you make binocular smart glasses?
Yes. There is no limitation. Basically, we're using a monocular solution today just because all this market is a new market, is just starting, and it looks like as a first type of such devices are being most likely monocular for all wearable. In comparison to the more high-end virtual reality, there's a full immersion for mixed reality, for high-end professional use cases. we are aiming to get the smallest, lightest, and the most power efficient type of display engine for an all-day wearable, which is very, very challenging because of almost a very small battery size. And it has to be very, very light. Otherwise, your, the temple arm on your ears are going to be painful. And if you want to think of a use case, I would say that first of all, as a customer, we saw the first one was Google, that actually it was North that Google acquired. And they came up with the first all wearable device with, I would say, bursts of information and messages, more or less the same use case like use your smartwatch today. But instead of course, picking up your hand and looking at your smartwatch, you will have it just in front of your eyes. So monocular at the beginning, and then as the market accepts that and more apps come in and the need for binocular for all-day wearable, we'll do that. Of course, there is no technology limitation in doing that at all.
So Ilan, there were two questions here. One question was if we can do the pre-distortion online or it should be offline.
So of course, what we show over here is for the sake of a quick demonstration. The pre-distortion actually is done, of course, online with the algorithm handling actually the stream of video that is coming in. And to be more precise, the actual location of where this algorithm runs is going to be on the application processor side of the device itself.
Okay, and another question that I saw here about the power consumption. So the question was, isn't it too demanding, 320 milliwatts for smart glasses, for all-day smart glasses? So how are you going to handle it?
So to start with, indeed, this is a starting point. And of course, when we look in the roadmap into the future, this number will be optimized because we will be able to reduce the number of chipset with a tighter integrated device with maybe tighter nodes in terms of a process technology for the digital domain. So the idea, of course, is indeed to get this reduced with new techniques and new different over the years. But what is the average on time, say, on the vector for the duration of the day? And we most likely talking about below 1 hour. So if I talk about an hour, the battery is that can a good fit for such a temple arm with the rate of
Yeah.
then you can see that this is a 3.7 volts. This will last more than an hour. So I think we're going to be in good shape for this infographic because it's not full immersion. It's not watching a movie. It's just getting notification, messages, navigation information, things that really want to have a quick, a notification about something that you need information while you're on the go in the most convenient way possible.
This is great. This is great, Ilan. We have someone in the chat wondering how do you handle or how do you remove speckles in the image?
So it's not needed because we don't project on the wall. We are projecting, we have a waveguide, and so this is not needed, this application.
You don't see speckles.
You don't see speckles
through waveguides.
Through the waveguide.
Speckle is a phenomena that is happening because of coherent light hitting a rough or a rough surface. And that's where you have the coherent light that is causing some of the rays, or the rays are reflected back from the projection surface, to be either canceling one another or augmenting one another. But that's because you have a rough surface that the light is hitting. When we talk about glass patterning and combiners like waveguides, we do not see that this is happening because of the nature of that specific waveguide that is not basically a rough surface causing any speckle to be created within the light channels of the waveguide itself.
All right, fair enough. Another question we have is regarding the safety concerns. for the driver that is out there driving, would the glasses be wearable? Wouldn't they distract him? Or what about
driving, you mean? You're saying if I'm driving in my car and wearing augmented reality glasses, whether this will be a distraction?
Right.
This is something that I truly cannot answer. I think that at some point, most likely that some administration or some government offices will have to look into that. I can see that maybe as an issue, but maybe there will be some, today, for example, today you have infotainment in your car, and the infotainment system is adapted such as that it will not cause any distraction to you while driving. So naturally, you will not be able to see any movie on there. Get out. The fonts are big. You have Android, for example, for car, or the version of Apple iOS car. And the application, the operating system you use in a car and making sure you're driving, etc. So maybe this will evolve for reality. Think of it as
like a heads-up display.
Exactly, like you used to have heads-up displays that basically augments the information on the windshield itself. But it's not causing you any distraction. It's actually causing you not to be distracted because you don't need to take your eyes off the road in order to see, I don't know what, if you have any hazard light that is coming on, or to see your speed, or to see navigation information. So augmented reality maybe will be a subset of a heads-up display specifically for driving. But this could be a wonderful application and time will tell. Without further ado, let's quickly go to the other lab before we disappear again. The other lab is our calibration lab, and we're going to see also some examples of the augmented reality frames and glasses. Here is Nir with us. Nir, could you present and introduce yourself?
Hi, I'm Nir, the system and firmware team leader. This is our calibration station. In the black box, we have our projector. We calibrate the MEMS mirror, opening angles according to the customer needs, control loops, safety. We can also calibrate the laser intensity and white point. To do so, we are connected via UART to USB, goes to our PC. In the PC, we have the calibration station. We can select what we want to calibrate and what not. We have the user interface. In the user interface, we can monitor and control everything that goes inside the projector. And we can adjust the, we can adjust the horizontal opening angle. We have a dedicated pattern that is generated inside the projector, goes to the camera. From the camera, it's go to the PC and analyzed in the PC. We can also adjust the vertical opening angle. We have a heat plate that we can calibrate over different temperatures. We can also control each laser intensity, the green, blue, and the red one. Let's go to the MEMS lights. And also, are you with me?
Yes, good. There was a quick question about the frame rate at different resolutions of what you have just shown.
The frame rate we are using is 60 frames per second, and the resolution is up to 720p. It also depends on the one that's sending the video.
Okay, thank you.
This is the basic. This is our AR glass demo. It was designed and manufactured by Quanta Computers in Taiwan. The glass waveguide was designed and manufactured by Dispelix. Both of them are our partners in the Laser Alliance. All the electronics and optical elements goes into the right temple arm. In case of a stereo, you can do the symmetric solution on the left one. Inside the temple arm, we have the PCB and we have the optical module. In the optical module, we have the MEMS mirror and the laser package include all three lasers. In the PCB, we have ST MEMS mirror driver and ST MEMS mirror controller. We have a ST laser diode driver and a photodiode. We have STM32 that control all the others, and we have FPGA that used for the laser and data path. We have HDMI input that goes to HDMI to MIPI input. The projector can get MIPI from PC or application. The output projection, it's going from here, and then it goes into input window of the waveguide, and then to output window to the viewer.
Very nice, thank you. Is there any questions from the audience?
Yeah, thanks, Alan. Wilfred from STMicroelectronics has actually multiple questions. Please go ahead.
Yes, thank you. Very, very impressive. I used to work on optical MEMS for over 10 years. So this was still the holy grail, what you're presenting now at the time. So I'm very impressed by what you're presenting today. I was just wondering, what do you use for the green and blue lasers now? Is it gallium nitride based or do you still need frequency doubling? Or
No, it's gallium nitride base.
Yeah.
In native diodes for quite a while now, more than 10 years, I would say.
Yeah,
and the
yeah.
blue one was invented by actually Professor Nakamura, that back then was at
Yes.
Michigan.
Yes, I met him once. Yeah.
Yes.
Yeah, and the green was still difficult at the time, but now it's available. Yes, yeah.
Actually, the improvement, I have to say that at the beginning, the wall plug efficiency of green were horrible.
Yeah,
they were
exactly.
1 to 2%, but now they got to a much more mature level. So now the light source is actually a all-in-one 3 diodes packaged together, red, green, and so we don't need to deal even with the TO CAN, like TO38 individual diodes. We have a package from Osram that is a light source.
From Osram, yeah, I saw that. It's in Sunnyvale or wherever. Yeah. Yes, I saw that package once. Yeah, cool. And I missed it before. The iBox is how big now? From the waveguide, you have to. Yeah, you said you're working with waveguides. Yes.
Yeah. So first of all, the micromirror can reach a much higher opening angle than even what is this waveguide. This waveguide supports a 30 degrees field of view diagonally with an iBox of 10 by 10. So a micromirror can get to even 60 or 65 degrees with the opening angle of the, the horizontal and vertical axes.
Okay, that's the advantage of the mirror, huh? Exactly. Yes. Yeah. Okay. Yeah. Of the scanner, I mean. Yeah.
Yep.
Cool. Thank you. Thank you, Ivan.
Yeah, you're welcome.
Thank you, Ilan.
So there is one more question from Jeremy.
Questions?
Yeah. Thank you, Ivan. Thank you for the presentation. I have a question. You mentioned several times laser alliance. You mentioned several times laser alliance. Can you tell us more about it? Oh.
Let me see if we can get the connection back.
Oh, now we can hear you.
Yeah.
Yes, Ilan, I think the question was about the laser alliance.
Laser power?
No,
laser alliance.
Laser alliance. Can you
Laser
Alliance. Laser Alliance. So would you like some information or introduction about Laser Alliance, or there was a specific question?
Can you tell us more about this, please?
Yeah, of course. So the Laser Alliance is a consortium that was founded by STMicroelectronics with additional members as founding members. It was founded about 2 years ago. And the idea behind it is to bring together companies that will collaborate with each other on different areas. to introduce laser beam scanning, LBS, as a solution for augmented reality. In the Laser Alliance, we have almost 20 members, I believe, today, and we're, of course, welcoming more and more companies. That covers all the way from component providers like STMicroelectronics for semiconductor. So, of course, we do micromirrors and the chipsets. But in order for that to build an augmented reality glasses, you would need additional partners to help you out. For example, you need a combiner, waveguide, reflective, diffractive, holographic optical elements. We're agnostic to that. We welcome different waveguide or combiner companies to join our alliance and to work with lasers. We need companies that would know how to assemble it, like quantum computers that Nir mentioned before. So the alliance brings different companies with different skill set and different products to work with each other. We have work groups that we share information about the market, about the technology, about what is needed, about the customers, in order to promote, again, the LBS solution for augmented reality all-day wearable, because we believe that by working together, we'll be able to come up with the best solution and the most advantageous solution as possible for the benefit of our customers.
Thank you very much.
You're
Thank you,
welcome.
Ilan. Thank you, Ilan. I think we're good to continue.
Okay, thanks. So we will thank you, Nir.
Thank you, Amir.
We spoke a lot about augmented reality and we spoke about smart glasses. What we didn't speak yet is other applications or other possible products that would make use of our micromirrors. And such an application, I showed it to you in the demo case. It was a time of flight lidar for a depth camera working with Intel. But today we're using a different, I would say, different solution, again, lidar, but for automotive and industrial applications, which requires a different architecture and a different set of products. So let's get into this lab over here where we have Guy. Guy is going to help us to present our offering for lidar solutions using micromirrors. Guy, would you present yourself and the technology?
Hi, my name is Guy Amo. I'm a system architect and a project manager here at STMicroelectronics. Our micromirrors can also be used for 3D sensing applications. Here in this unique project, a consortium of companies led by LeatherTech, we have put together a LiDAR development platform for automotive. What ST contributed to this unique project is an entire transmit module, a scanning transmit module. Here you can see the structure of the optical module of the transmitter. This transmitter couples a high power laser from Osram, and we have designed the entire assembly and optical path to produce a unique scanning pattern. The scanning, the beam shape that is required by this optical module is actually a line and not a spot, which has a divergence of 6 degrees in one axis and 0.1 degrees on the other axis. Here you can see an illustration of the inner structure of the optical module, which has a group 1 lenses, then a group 2 lenses, and then after the mirror, a group 3 lenses, which shape the final output beam. On the top here, you can see a demonstration of the first stages in the integration, a 3D image taken by the sensor. This image was taken in a low power configuration, which only used like around 10% of the maximum optical power. This platform is highly robust and can provide various configurations which trade off between resolution, frame rate, range, and field of view. The maximum field of view that can be achieved by this system is 120 degrees by 24 degrees. In other configuration which narrows the field of view, we can reach to longer ranges and higher frame rates. Here you can see the MEMS mirror. This is a 3 millimeter gold coated mirror, which is best suited for IR wavelength, together with the driving electronics. This is the actual mirror and electronics which is integrated into this sensor.
Is it the same micro mirror guide like we use for augmented reality?
This is a slightly different mirror. It has a lower resonance frequency of 2.1 kilohertz. It is slightly bigger than the one used in AR, and it is gold coated rather than aluminum coated.
And the electronics?
The driving electronics is basically the same, same as the resonance of the AR application. Here we have more flexibility, though. We can drive the mirror off resonance, since this is a lower Q mirror and we have slightly higher bandwidth. This mirror was designed to open to the full extent at 15 volts, and the PZT technology can withstand up to 40 volts. So we have some margin, and we can drive the mirror off resonance and still achieve the full opening angles. Here you can see a LiDAR development kit. ST provide this kit for companies that want to develop their own LiDAR. So basically, it's the same configuration as we used in the LiDAR project, but can be configured in differently and can be optimized to other systems and other architectures. Here, in this station, you can see a calibration setup in which we calibrate, we trim the analog front end and calibrate the sensor sensitivity using image processing algorithms. We also calibrate the system over temperature in order to have a stable opening angle and provide accurate sensing of the mirror throughout any environmental conditions, such as changing temperature or air pressure.
Great, thanks, Guy. Would love to hear.
Very good. I have one question. I'm sure that there are others as well. So
Sure.
you're steering the beam using your mirrors, or are you using any other type of beam steering technology?
Excellent question.
Good question. Yes. So this is a hybrid flash technology. Basically, the MEMS provide only scan only a subset of the full field of view, just 7.5 degrees. The rest of the field of view is achieved by a digital beam steering device, which is a technology of LeatherTech, which further extend the field of view to 180 degrees. Together with a detector array, the other axis of the 2D scanning is resolved.
So that the digital beam steering, is that phased array? Can you tell us, or?
It's a liquid crystal polarization grating technology.
LCPG.
This
Thank
is a
you.
transmissive kind of LCOS solution.
LCOS. So it's in reflection. It's in reflection, not in transmission.
Transmissive. It means that light will
LCOS?
pass through. Yes.
Ah, infrared. You can go in transmission. Yes, with LCOS. Here we go. Yeah,
There
yeah.
are two
Okay.
types of solution, either reflective or transmissive. This one is a transmissive one, which LaserTech licensed from an American company, and it's their offering for as a solution within the what is called Accelerator platform, or they sell it also as a steering device as a separate product. You can find further details of that on LaserTech's website. And the image that Guy showed over here of a guy playing basketball, which was part of a demonstrator that they actually did in Canada, you can find those clips if you just type Accelerator or LaserTech on YouTube. You will get to see all those nice clips and showing the resolution, the acquisition time, the frame rate of the different demonstrations that they did using this platform, which is going to be released to the market pretty soon and going to be displayed on exhibitions by LaserTech and STMicroelectronics in the very, very near future.
Well,
Thank you, Ilan.
excellent. So,
Thank you.
so from
Very impressive.
glasses to a LiDAR for automotive, this is quite a range of products.
Yeah, there are so many other applications that we haven't talked about, but they were part of laser beam steering or our installed customer base today. Companies that are doing, for example, AccuVein, Vein Finder. I don't know if you ever saw that. It's a device that can point on your hand. It has an infrared camera. It can detect the blood flow in your veins. And so for, when you go to a clinic and they need to do some kind of an in vitro treatment to take blood, draw block, or insert maybe a needle. In some cases, for people, it's quite painful and difficult to find a vein, and this is a vein finder. It knows where the blood flows, and it projects back the map of your veins in green color. And a medical device using LBS, one of the applications that we have customers from, so it could be really from consumer, medical, automotive, industrial, you name it. A lot of use cases for micromirrors.
Excellent. Very impressive. I've just heard about that vein finder. That's amazing. So
yeah. It's called AccuVein. Have a look at that. It's actually quite interesting device.
Very good. And Ivan, I'm sorry I cut you off. Please excuse me for interrupting you.
Oh, thank you, Tracy. Those are very valid questions. We're all interested. There were a few questions. Julian from 2.6, would you like to ask your question yourself? Or if not, there is also Florian from XR Nanotech. You can just go ahead and unmute yourself.
Oh, yes. Hi, thanks. I wanted to ask, how does the sensor system mitigate sunlight or even direct sunlight, which is probably a big problem in the automotive sector?
Yes, that's a good question. The digital beam steering device is working both on the transmit path and also on the receive path. This way, the field of view seen by the detector is narrowed down to the region which we scan. This further enhances the SNR and reduces the noise from the sunlight.
Okay, thank you. And Frank from Instrument Systems, your question?
Yeah, I just heard that you're talking about polarization. So is it needed that the beam is polarized, or?
No, the PDSD is actually it's just a beam steering device. It able to change the polarization of the material to steer the beam to different directions. So you control it by electrical voltage, and then you change the polarization of the material inside, and it
Redirect
the beam.
Deflects.
Yeah, deflects the beam.
Yeah.
Okay.
Also called surface, right? Or, yeah.
Okay, thank you, Frank. Yeah, Ilan, please go ahead.
Thank you, Guy. This was really
Thank you very much,
interesting.
Guy.
Thank you for the great questions. And let's continue. So we saw the electrical part, we saw the system part, we saw some software, we saw a different application, which is LiDAR. We saw just a snapshot really quickly of the micromirror, but I'm sure that you're dying to see much more of that. So we're going to go into our prototyping lab, where this is the place where we are basically handling the micromirror themselves under controlled environment. We have here with us Shlomi, that is going to walk us through the different equipment and tooling and procedures we do over here. Shlomi, would you introduce yourself and show us the good stuff?
Hi, hello. My name is Shlomi, and I'm an optical engineer. And I would like to introduce for you our main labs for mechano-optical assembly. So let's go through basic stations, and I will introduce the key points of this lab. So here actually we store our wafers of the MEMS mirrors. This is a special desiccator with the controlled humidity and temperature. So I will open, show you the example of the wafer. This way we receive it from our fab, ST fab. So here, if you zoom in, you can see small MEMS mirrors. Each one of the mirrors actually will be used in building of our prototypes.
So I guess this part over here are mirrors that you already took out of the wafer, right?
Exactly.
And all the rest are mirrors that are still available for you to pull out.
Yeah, exactly. These ones, the missing parts are actually already removed, and we use in building of prototypes. Sometimes some of them can be damaged, stretched, so we just make an observation under microscope, visual inspection, and we choose the good units
before you go into
before we go through all the steps of our process. So I will introduce to the next step. So this one is a specific one, is a small round mirror, and of the diameter of about 1.1 millimeter. So this one is a resonance mirror. We can distinguish between resonance and linear mirrors by the shape and the size. So the linear mirror will be a rectangular shape, bigger size. Resonance mirror will be round shape and smaller size.
Those are thin film? This is thin film, or what kind of actuation? Is it thin film mirrors?
This one is electrostatic.
So this is from the previous generation.
Yeah, this one exactly. It's the previous generation. We have modern the mirrors of modern design that are piezoelectrical mirrors. So,
but the shape of the wafer, the size, and the structure and the grip ring is the same, right?
Yeah,
also an 8-inch.
Yes, it's 8-inch wafer. Some standards that are used in fabs actually. So this is a small introduction of the wafers and the MEMS mirror as it's located on the substrate. Okay, and we'll go to the next station. We call it probe station. So the main goal of this station, we can take any wafer and to use specific, very special probes and equipment. We can operate any single mirrors on wafer. So here we took example, just a small simulated mirror.
Can the audience see the mirror below the microscope?
Yes, it's good.
Good. Show the screen.
Okay,
Yeah.
so now you can see it magnified on a screen.
Yeah, here we have a very high magnification of about 100 times, I think at least. And we can see the main part of the mirror. So I can point with my finger. So this one actually clear aperture. This is a reflective part of the mirror. Actually, the laser beam will be reflected from this side, okay? From this surface of the mirror. And here we can see the actuator part, and we can see small square pads, electrical pads. Actually, we will perform the wire bonding to these pads in order to operate the mirror with dedicated electronics.
So this black thing over there is the probe, right?
Yeah, actually you can see.
You're touching the pad to actuate it, yeah?
Exactly, this is a little bit shadowed, but this is the actuator. You can see it in the normal size. I think already Terry showed it before, and here is just magnified, and it's touching the probe, and we can apply voltage specific parameters, and we can test the mirror and to test the basic parameters such as frequency response and the opening angle.
So this micromirror
So we
has,
can-
this
yeah.
is a thin film in micromirror using thin film actuation. You
Yes.
showed the area of the actuator, but I saw a question about if we have piezo-resistive material as well. And yes, we do. Part of the piezo-resistive material is next to the spring, and it will monitor the stress of the spring. And based on that, we will know what is the opening angle or how much the mirror is tilted, because that piezo-resistive will translate the mechanical stress into electricity.
And if you remember the first diagram for the first lab, you could see that we use it as a feedback for our
Exactly.
control.
So the piezo-resistive material is our sense. It is available on both mirrors, the resonant and the quasi-static. And with that, we are able to what is called close the loop on the mirror control to know how much we need to adjust the micromirror if it's out of the scan, either frequency or opening angle. So it will be a correction or corrective procedure to keep it within the specification it's meant to operate. And plus one, of course, very, very important part of that is also for safety. So in case that the mirror doesn't operate at all, it will give you an indication that the mirror is malfunctioning, so you know what to do in that case, depending on the applicative, of course, use case and decision.
Yeah, so this station actually helps us to decide to make like a sanity check, as you described with all these details, to make a sanity test and to decide, can we go to further steps and to continue the process of the prototype build and testing.
Just one point to mention, part of what we do in STMicroelectronics for all MEMS products is something which is called EWS. EWS is electric wafer sorting, which means that after we manufacture the wafer, they will pass an EWS station with probes that are going to check to validate that the actual mirrors on the wafers are operating as they should. And there are no any electrical problem like leakage, etc., that might indicate that there is a problem with the manufacturing of that part. And next is automated optical inspection, which again, it's a Falcon tool we use in order to detect if there is any problem optically with the mirror, blemishes, scratches, particles, or anything that might happen during the fabrication process when we fabricate the mirrors itself.
Okay, so let's introduce another key points of this lab. So once we choose a specific mirror from the wafer and we want to continue with the normal build, normal process, so we can extract, as you already saw on the wafer, some parts are empty, so we extracted these mirrors and we take to this station. This is the main assembly station. Here we can take the simulated mirror and to place it on the specific substrate. Here is an example of the resonance mirror, and it's already glued to metal substrate. You can see the magnified image on the screen. We actually observe it with the digital camera through the microscope. So it's a magnification about 40 times, I think. So you can see here actually the active area of the mirror, the actuator, the pads. Here already some wire bonding is already done, is already performed. So this is a good example how the mirror is positioned and glued to substrate. We have some reference points like hard stops, we call it, so we can make very accurate position of the mirror according to tolerances that we can absorb. Okay, so this is example. Just in a few words, I wanted to say that because ST provides the complete reference design to our partners and customers, so we need to take care of the entire build of the prototype. So it starts here with the optomechanical part. We build everything. We just insert all the components, such as laser diode, passive elements, reflective mirrors, static reflective mirrors, not only MEMS mirrors, lenses in the dedicated housings. So we put everything inside and we build the prototype of a very small size. This is a good example of our Helen optical engine that contains all the elements that I described right now. So this is a very small dimensions of about 14 by 12 by 6 millimeters. So this is very small. And more.
What is the volume?
About 1.1 millimeter. cc. 1.1 cc. Okay, so this dimension requires a very gentle and accurate assembly under the microscope. Most of them done under microscope. So here, this is the wire bonding station. Here we actually perform the wire bonding, the electrical connection between MEMS pads and electrical flex cable. Okay, so here I can introduce how exactly I do it. Okay, by manipulating this machine with a dedicated mouse. Actually moves very special probe on the specific points that I want to connect. So actually it will be pad on the electrical flex cable and the pad of the MEMS mirror. Okay, so I will demonstrate it. First of all, I will do the first point. So I solder a very thin gold wire of about 25 micron of the width to the pad of the electrical flex. And then I will move it to another location to pad of the MEMS. Okay. I will fine tune the height and the XY position, release the button, and it will be connected. Okay. So in this way we perform it here, just manually one by one. Sometimes it can be several wire bond connections. Sometimes it goes to up to 9 or 10 connections on the same assembly. So it depends on the model that we use. And this is very accurate, precise work that requires a lot of patience.
Thank you, Shlomi. It was great. So
Yeah.
basically, all the different toolings and procedures that we do over here is starting with our own design, often, as Shlomi said, optical engine to host our mirrors. We do all of that simply because we want to help our customers be much quicker. So once we develop the overall optomechanical electrical reference design, we can help our customers by providing to them something that they can start with. And we would provide to our customers the reference files, 3D models, procedures for assembly, procedures for bonding, and everything that they need so they can take it to their own mass production facilities. Because of course, all of that is for prototyping and it's manual, but that's how we develop the right procedure. And from there, we can take it to full manufacturing or to be able to move it to a full manufacturing cycle where everything, of course, is automated with pick and place machines, with machine vision, etc. That is done by our module makers and EMS companies, like, for example, quantum computers. That was great. Thank you, Shlomi. I think
You're
that
welcome.
we
Yeah.
saw how we handle our mirrors and wafers. What we're going to do next is to see how we deal with the optics side. So once you have multiple of diodes, red, green, and blue, you want to make sure that they are collimated and combined correctly. So let's go to the other lab, which is the optics lab, and we can see how this is done. So,
And before we leave, I would like to say Toda Rabah to Shlomi, and also share a comment from one of the audience members when you were first showing the magnification, the microscope view of the mirror. The comment was remarkable. So, and this whole lab is truly remarkable. So thank you so much, Shlomi.
Thank you, Shlomi.
You're welcome. Yeah, it was a pleasure to introduce it for you guys. Thank you. Okay.
pass. And let's go to the optics lab where we have Alex waiting for us.
Hello.
Our last presenter for the day.
Yeah.
Alex, please introduce
Hello.
yourself and what you do
Hello,
over
my
here.
name is Alex Dometz. I'm a optic team leader in ST Israel, and we are here in this lab. We align the optical engines. In order to ensure best image quality, we relay type optical tolerances, including alignment of the laser light source to the MEMS scanner. Such panel alignment done with the 6-axis stage ensures best beam quality. So here we can see the 6-axis with the vacuum tip hold the collimation lens.
Just a moment, let the camera focus. Okay, now we can explain.
Yes, so we have here the vacuum tip that hold the collimation lens, and we operate the laser and we start the collimation process. Our collimation process, usually we collimate in FPD infinity, and we measure the beam size in several distances. You can see here in this screen the collimated beam. Collimated beam, just 1 second, this one. And we measure the beam size with the beam view camera. Usually our beam size is around little bit collimated. Okay, so now we can see that the beam size is very small. It's around 0.6, 0.7 by 0.5 millimeter. For example, we measure it now in 300 millimeters, and you can see here the spot size. So after we finish the alignment of the collimation lens, for example, for the RGB applications, we repeat this step for other lasers, for example, red and blue. And once we done this alignment process, we operate the MEMS mirrors, be sure that our MEMS work properly. And finally, what we do, we just screen some patterns to be sure that our optical engine is alignment well, it's collimated, it's in focus, and the sharpness good. So, for example, now you can see here the monochrome application, just a green laser. But as I said, we can collimate other lasers for color application.
Yes, just for the sake of the demonstration, we use one.
Yes, yes.
One laser.
Yes, right. Right. Okay.
So
so
thanks,
any
Alex.
questions?
Ivan, is there any question on the chat?
So I have one. Is this done for every element produced, or is this done once for a batch?
It's a good
This
question.
alignment?
The active alignment needs to be done, of course, for every module that you build. But again, here we do it on a manual basis with a 6 degrees of freedom access. Once it goes to production, those active alignment are done by automatic tools.
Yes, it's pick and place and the automatic tools. The 6-axis we have here, the 6-axis automatic stage. But
you have also in the office
yes,
a motorized
we
stage.
have a motorized stage,
with
automatic
machine
stage.
vision
Yes.
option.
But here we build the prototype, so we use with the manual 6-axis stage.
So you don't have to do this manual process for every batch. So you do it initially for the prototype, and then it's automated for the production. Yes?
That's right.
Right.
That's right.
Yes.
Here we develop, this is an R&D center where we develop the initial, call it procedures, steps. But of course, once this is done in terms of a proof of concept, then we leave it to the expert companies like Quanta to take it to full production, because this is what they don't know how to do.
Yvonne, do we have any more questions?
Yeah, thank you, Ilan. I was wondering, so if this is automotive qualified, and to which standards?
So that's a good question. So when you looked at the lab that guided the presentation for LiDAR, he presented a micromirror which is different, a 3 millimeter gold coated, and then he said that the electronics are the same. The electronics is the same in terms of the building blocks, but the qualification is different. That electronics part will be qualified for automotive. We are talking about the qualification of ACQ, call it 10X, 100, 101, 102. And that is going to be qualified when it's ready to go to full manufacturing. The overall reference design and the prototype is qualified for ASIL, I think, B, safety standard.
Okay, crystal clear. We have a question from Infineon. Bettina, would you like to ask your question?
Yes, thanks, Ivan. So does it mean also that you are targeting AR head-up display as applications with your MEMS micromirror?
If we are targeting heads-up display applications?
Yeah, for automotive, yes.
The main markets for us today is augmented reality, all-day wearable, and the later one. Heads-up display is an option, of course, but we are limited for this application, not because of our micromirror, but because of the light source offering. So for heads-up display to work in the daylight and full sun, without, of course, because there are some standards of how transparent the windshield must be. So you cannot put like a black sticker and avoid the sunlight. That's not going to be legal. It has to be transparent up to a certain point. So what is limiting us is basically the light source. It's not the micromirror itself. It's the availability of light source that can support the luminosity of, I don't know what, 500 lumens at least in order to be really useful. And that is simply not available in the market. So this is not really an application that we're targeting.
Okay, all right. Thanks a lot.
Cool.
Okay, thank you.
Thanks a lot, Alex.
Thank you,
that was
Alex.
great.
Thank you.
So I think this was the last presentation for the day. We are going to move to the section of questions and answers into a different room. While we do that, we have another video for you, which is Lab in the Fab. Lab in the Fab is a new offering from STMicroelectronics. It's a collaboration between 3 companies. It's STMicroelectronics, the Singaporean technology center, which is called IME, and a tool vendor, which is Evatech for semiconductor MEMS tooling. And together we have built something, a new concept, which is called Lab in the Fab in Singapore. We have already a fab in Singapore, quite a big one for MEMS. Now we're going to take a section of it and we're going to build some kind of an R&D rapid prototyping fab, so we will be able to be more agile and shorter cycle time in diffusion. There's something new that is happening today. We are inviting partners and customers to come with us and prototype advanced MEMS technologies for different applications, including micromirror. So let's have a look in this video clip while Dadi and I are going to another room to have the questions and answers for the final session.
Wow, this was exciting. Thank you very much for watching us, and please subscribe to our channel, like this video, and I will see you next time. Goodbye.